Right now, the modern world runs on an invisible, microscopic foundation. Everything from AI data centers to fighter jets depends entirely on advanced microchips. But this vast digital network is incredibly fragile. Even though the United States designs many of these advanced chips, roughly 90% of them are actually manufactured on the island of Taiwan. Looking at this map, we can see massive international trade lines radiating out from a tiny node in Taiwan. If regional conflict broke out involving China, these supply chains would flash red and disappear almost overnight, cutting off the global tech industry from its most vital component. To prevent a total freeze of the global economy, the U.S. government is investing billions of dollars to try and rebuild domestic chip factories and bring manufacturing back to American soil. The U.S. actually invented semiconductor chips in the 1950s. For decades, American companies like Intel completely dominated the market by optimizing their factories to build processors for bulky personal desktop computers. But in the mid-2000s, Intel made a massive strategic error. Apple approached them to manufacture chips for a new, unproven pocket-sized device. Intel walked away from the deal, betting that PCs would remain the center of the computing universe. This split bar chart illustrates the financial fallout of that decision. While Intel split its capital between designing chips and manufacturing them, Taiwan's TSMC poured 100% of its budget directly into manufacturing upgrades. By focusing entirely on building exactly what outside designers wanted, TSMC captured around 70% of the entire foundry market. Intel is now fighting to reverse that multi-decade decline. Reclaiming the top spot requires mastery over a physical environment so sensitive that a single microscopic speck of dust would derail the entire operation. This is Intel's Oregon plant, the center of the American comeback effort. It operates as one of the most tightly controlled fortresses on Earth. To protect the silicone inside, this facility is kept 1,000 times cleaner than a surgical room. Because a standard room has millions of floating particles, the factory actively sucks human hair, skin cells, and stray dust down through thousands of holes in the floor in under a minute. But physical particles are only one threat. The materials used to build these chips are highly sensitive to standard white light, forcing the entire factory floor to be permanently bathed in a surreal, heavy yellow glow to block out ambient ultraviolet rays. Even subtle vibrations from footsteps can ruin the intricate patterns printed on the chips. To stabilize the facility, its foundation is poured with twice as much concrete as the world's tallest building, the Burj Khalifa. The base layer for all this engineering is a thin slice of silicone cut from sand. Before a single chip can be built, these dark, pristine wafers must be refined to 99.9999999% purity. These paranoid physical defenses are completely necessary. If a wafer is only 98% pure, or a rogue speck of dust lands on it, the contaminants interfere with the electrical connections on the chip. In an instant, a mistake turns millions of dollars of raw silicon into literal garbage. The core component being built onto that silicon is the transistor. It acts as a microscopic electric switch that turns current on and off. To make chips faster and more power efficient, manufacturers have to pack up to 10 billion of these transistors into a space roughly the size of your fingernail. There is only one machine capable of printing structures this small efficiently. Built by ASML, a single unit costs $400 million. Deep inside, it generates rare ultraviolet light, using lasers to draw complex, atomic-level patterns directly into the wafer. A wafer spends 3 months traveling through thousands of automated steps before it is finally sliced up and acoustically tested for defects. The percentage of these chips that actually turn on and work at the end of the line is what the industry calls yield, and it is the ultimate metric of a factory's success. Consistent, superior yield is exactly why the biggest AI designers in the world, like NVIDIA, still rely on Taiwan to manufacture their most advanced technology. Buying expensive machines won't save Intel's foundry business. To survive, they have to perfectly integrate thousands of these tools into a seamless process flow that achieves near 100% yield. As this diagram shows, atoms can only be squeezed so close together before they physically overlap and fail. The semiconductor industry has scaled down devices for decades, but standard silicon is now hitting its absolute atomic limit. To push past this physical wall, researchers inside Intel's R&D labs, working in what is essentially America's test kitchen, are experimenting with unproven elements across the periodic table, trying to find new materials that can augment or completely replace silicon. The explosive rise of AI is acting as a forcing function for this research. AI data centers demand massive amounts of power and speed, requiring next-generation materials that can handle extreme thermal heat without melting the processor. The race to find the perfect chemical mix is happening in both the US and Taiwan. Whoever successfully scales and commercializes these new materials first will dictate the future of the global AI economy. But there is one final vulnerability that physical technology cannot solve. Running these advanced machines and researching new chemical compounds requires a hyper-specialized global workforce, talent the US is currently struggling to secure. Geopolitical friction and strict, expensive new restrictions on the H-1B visa are making it harder to bring in skilled foreign workers. As a result, American tech companies are being forced to spend heavy resources on upscaling domestic talent entirely from scratch. Shifting the center of technological gravity away from Taiwan is not a quick political fix. It is a multi-decade crusade requiring hundreds of billions of dollars to control everything, from international borders down to the movement of a single atom.